xt will be equal to 3 of x of t minus 1 minus 2 to the power of t. This is the recurrence that we have to solve. Okay, and I'm looking at my cheat sheet again. So what did I tell you that we always have to do before we move on with an exercise? We have to identify our A and our B. What is our A? A is equal to 3. It's the term connected to x of t minus 1. So A is equal to 3. And our B has this form, 2 to the power of t, which is interesting. I will look again in my cheat sheet because I have to find the solution of this equation. And I see that the form of B that closely resembles what I have, which is 2 to the power of t, is the last one in the table, B multiplied by R to the power of t. That resembles my form very, very closely because B could be 1, the ratio R is equal to 2, and T is equal to 2. Therefore, that is exactly the form that we're working with. What does this mean for us? It means that I can create my hypothetical solution x star of t, which is going to be equal to what? According to the table, if my t looks like b multiplied by r to the power of t, my solution will look like c multiplied by r, which in our case is the 2, to the power of t, like that. So this is our solution form, c multiplied by 2 to the power of t. Again, how did I obtain this hypothetical solution? Looking into the table of the all solutions possible. Great. So this is first step. First step, which leads us to the second step. In the second step, remember that we had to rewrite our equation according to the solution that we found. If my solution xt is equal to c multiplied by 2 to the power of t, then in this original recurrence, I will go ahead and replace this term with what I found here. However, please pay attention. The difference between this exercise and the one that we did before is that our term b now is not a constant anymore. It's something dependent on t, okay? If it depends on t, it means that this equation will change according to the order of the t that you're working with. Therefore, xt will be equal to c multiplied by 2 to the power of t, and x of t minus 1 will be equal to c multiplied by 2 to the power of t minus 1, because this solution depends on t, which is different from what we had done before, where our solution was a constant. If your solution is a constant, then this constant will be equal to all of your x terms in the equation. However, if your solution depends on t, then it means that this t will change according to the x that you're working with, so to the element x, okay? Therefore, we can rewrite our equation, our recurrence relation xt is equal to 3 x of t minus 1 minus 2 to the power of t as c multiplied by 2 to the power of t is equal to 3 multiplied by x of t minus 1 is c multiplied by 2 to the power of t minus 1 minus 2 to the power of t. Like that. So literally what we do is rewrite the recurrence relation according to the solution that we found in the first step. And now we will solve and try to find some values for c. How do we do that? Well, when I see an equation like this that is two-sided, I like to take everything, move it all to one side, see if I can work with those values somehow. So what I'm going to do is move everything to the left and basically remain with an equation that is going to be equal in 0. C multiplied by 2 to the power of t minus 3c multiplied by 2 to the power of t minus 1. This minus will then become a plus 2 to the power of t is equal to what is left on the right side, which is nothing. So it's going to be equal to 0. I have this equation now that I have no idea what to do with. So when I don't know what to do with an equation, what do? I give it a common factor. The only common term that I have between all of my terms here is 2 to the power of t minus 1. I can give 2 to the power of t minus 1, a common denominator between all of these terms. 1 second, I see the chat popping up. Okay, so Simone was asking us what is B. If you look in the theoretical formula of your recurrence relation, B is the term that is added or subtracted at the end of your equation. So you have xt is equal to A, which is a constant, multiplied by your x of t minus 1, plus a B, something B that is a term that is going to change in your equation, which can take multiple forms, as you have in the table. It can have that form of a constant, so it can be a B, like we had in the first exercise where our B was a 4. It can either be dependent on t, like B multiplied by t, for example, if we had 2 multiplied by t, or it can take the third form, which is B, another number, multiplied by a ratio, which is powered to the power of t, okay? So for this example, yeah, that would be B. Exactly. Because that's your B, your solution will take the form C multiplied by R to the power of T. Because that's what's written in the table. So when we identified our B, we can also identify our solution according to the form that B takes. Okay? Is that a little more clear now? Yeah? Okay, perfect. Doesn't C multiplied by 2 to the power of t minus 1 in brackets? No, of course not, because it's a multiplication. And 2 is powered to t minus 1. Okay, so that's a power that has nothing to do with the actual multiplication. So t minus 1 is the term of the power. So it doesn't have anything to do with the actual multiplication. And we don't need brackets because it's all products. So when we have products, we know that that's the first relation that we have to take care of before summation or subtraction or anything else. Okay, so now that we've addressed those questions, I'll start from the beginning because I feel like I've lost a little my train of thought and I don't want you guys to feel lost, okay, when I'm explaining. So we've determined why our solution x star of t is equal to c multiplied by 2 to the power of t, because this is the form of our b, and according to the form of our b, our solution should take this form. The second step lets us know that we have to replace in our recurrence relation the solution, the hypothetical solution found in the first step. Therefore, instead of xt, we write c multiplied by 2 to the power of t is equal to 3 multiplied by c multiplied by 2 to the power of t minus 1. Why t minus 1? Because that's the term of my x. T minus 1, it's not t. It's t minus 1. Minus 2 to the power of t. All I've done since then is take everything to the left side of the equation and make this equation be equal to 0, so I can actually work with it and find some solutions for it. And I was left letting you know that the only thing I can do when I am having this sort of equation where I have a lot of powers and I don't know the power of my terms is give them a common factor. The only factor that is common between all of these is 2 to the power of t minus 1. Why? 2 to the power of t is equal to 2 to the power of t minus 1 plus 1, correct? Therefore, we can give this as a common denominator. 2 to the power of t minus 1 multiplied by what is going to be left out of every one of the factors. So if I were to take 2 to the power of t minus 1 out of c multiplied by 2 to the power of t, what I'm going to be left with is c multiplied by 2 minus 3 multiplied by c multiplied by 2 to the power of t minus 1. When I take 2 to the power of t minus 1 out of this equation, I'm left with 3c plus, when I take 2 to the power of t minus 1 out of 2 to the power of t, I am left with a 2 to the power of 1, which is a 2. This should be equal to 0. Our term that is dependent on t shouldn't affect the result of our equation, which means that we always look for c so that the equation is 0. Look for c so that equation is 0. So what is left in this equation? We have 2c minus 3c plus 2. That will be equal to 2 minus c is equal to 0. Therefore, our c is equal to 2. And that's good. We found our constant c for our solution. What do I do next? Now that I found my c, I can rewrite my x star of t. X star of t is equal to c multiplied by 2 to the power of t, which is what? C is 2 multiplied by 2 to the power of t. And this is my hypothetical solution. With this, I move forward to the third step. The third step of my equation will tell me what? That I have to look for the homogeneous part, yt, which is going to be equal to alpha multiplied by my a to the power of t. Remember, this was the formula for the homogeneous part. I don't know alpha, but I know a. Therefore, I can rewrite yt as alpha multiplied by a, which is 3, to the power of t. Like that. Which brings me to the fourth step and final step of the exercise. In the fourth step, I have to write the final version of the solution xt. So the final version of the solution xt will be equal to, hypothetically, it should be yt plus our x star of t, which means that our xt will be equal to yt is alpha multiplied by 3 to the power of 7, 3 to the power of t, plus, where is it? The term of my, I lost it, where is it? The term of my, plus x star t, which is 2 multiplied by 2 to the power of t, following exactly the equation. And this should be true for all t bigger or equal than 1 and all real alpha. And this is how we solve the exercise. And now I see there's some things going. Isn't it 2 to the power of minus 1? No, t is bigger than t minus 1, right? So when you do 2 to the power of t divided by 2 to the power of t minus 1, remember that when you do divisions of powers, the powers will actually become subtracted from one another, okay? So I'm going to try to explain this a little bit. I'm not really good at explaining powers. It's not my strong suit, but I'm going to try. When you have 2 to the power of t divided by 2 to the power of t minus 1, what you're actually calculating is 2 to the power of t minus t minus 1, correct? Which is what? 2 to the power of t minus t plus 1. Because you get t minus t, and then minus with a minus becomes a plus, which makes it a 2 to the power of 1, which makes it a 2. And that's how I get to this calculus. I still don't understand the logic of 2 to the power of t minus 1 multiplied by c multiplied by 2. I'm not exactly sure what you mean by the logic of that. Would you mind turning on your microphone and letting me know, because I don't understand exactly what you want me to explain.
You have c times 2 power c times 2 to the power of t, and then you write down 2 to the power of t minus 1 times t times 2, but I don't understand how that comes out of c times 2 to the power of t.
This one?
The first part, yeah.
Okay, so in here, what I had done, I had created a common denominator between all of my factors. So a term that is common for all of them, something that I can multiply each of these terms with, and it's something that I can multiply all of these terms with, basically. When you do a common denominator, it's as if you were to divide by that number. Okay, only instead of actually dividing by the number, you will write it in front of your parentheses. So when you divide c multiplied by 2 to the power of t by 2 to the power of t minus 1, you are creating a fraction on which this is your upper term and this is your lower term. C multiplied by 2 to the power of t divided by 2 to the power of t minus 1, because it's a multiplication between c and your power, will remain c multiplied by the product of your division. And the product of the division, I have explained it right here, of how we calculate t to the power of 2 to the power of t divided by 2 to the power of t minus 1. This is a little bit of power calculus, which is some algebra that we should be familiar with right now. So this division right here of the powers is why I obtain in the end 2 multiplied by c. When you divide these two, it's like you're creating a fraction between them. I'm going to try to explain it in another way. I'm going to try to write it like this. C multiplied by 2 to the power of t divided by 2 to the power of t minus 1, like that. So because here you have division and here you have a multiplication, it means I can basically divide any of the numbers with any of these two numbers, either c or the 2 to the power of t, by my lower part of the fraction, right? Because that's the logic behind calculating fractions. So when I divide 2 to the power of t by 2 to the power of t minus 1, I obtain 2 because of this explanation. Therefore, this and this will cancel each other, and here I will be left standing with a 1, which will become c multiplied by 2 to the power of 1, which is 2. Therefore, I will obtain in the end 2c. It's not really something complicated or something that I have done particularly that follows an algorithm. It's just calculus. So this part from here on down, just calculus. I hope it was a little bit more clear. If it weren't, then text me even right now so I can send you some more exercises so you can practice with these divisions, with the with these divisions, with the powers and the fractions, because I'm not exactly sure how likely it is that you're going to get an exercise exactly like this in the exam, but it's some algebra that we should be familiar with. So if you need a little bit more practice, let me know and I will find some exercises for you to do, okay? But if the algorithm of how we solve the recurrence is clear, then I can move on with the next part of our exercise.
Maybe I have one very quick question. In the how we're going to say it, like the second paragraph from the bottom with calculations, and then the second row, there's 2 to the power of t minus 1, and then times c times 2 minus 3, and everything. But I was wondering if what we did is divide the line above by 2 to the times t to the power of t minus 1, why is 2 to the power of t minus 1 still in front there?
We're not dividing it. We're giving it a common denominator, common factor.
Okay.
So the logic behind it is that what is left in the parentheses is left as if you were to divide everything by this term. However, you can't divide, therefore you put it in front of the parentheses. When you open up the parentheses, if you multiply 2 to the power of t minus 1 by each one of these factors, you will actually get to the original equation. That's the logic behind it. This is it's a mathematical trick called common factor, I think.
Yeah. Okay, no, cool. I do think I know that one. Okay, no, thanks. I didn't see that. And then to get C, you can just omit like the 2 to the power of t minus 1. So you just focus on what's in the brackets.
Exactly. So the logic behind it is that every time we get to this equation that is written in terms of t and c, we always will look for a c so that the equation is 0. We don't care about t because t can be any number.
Okay.
Because t represents the term of the number, the position of your element in the sequence. Therefore, t can be anything. So we don't care about it. All we care about is that we find a c so that this particular equation is 0. That's its argumentation. Is that a little bit more clear now?
Yeah, there is. And maybe one final question. So how did the C that we got, because we were left with 2C minus 3C plus 2.
Yes.
So we just took the 2, I guess, to the other side, which made it minus 2.
Yes.
And then, maybe it's a stupid question, but what did we do from there?
From here?
Yeah, so like if you have the 2C minus 3C, oh, wait, no, it is a stupid. I see now. No, I'm sorry. I get it.
I just did the calculus. Only I didn't want to write minus C plus 2.
Yeah, of
I
course.
have to inverse them so it looks a little bit more pleasing.
Yeah, no.
Same thing as being written minus C plus 2 is equal to 0.
Yeah. Okay, cool. I get it. Thank you so much.
Okay, no worries. Okay. If everything was clear now for everybody and we have no more questions, let's finish exercise 4.3 so we can move on to Markov chains, okay? So this exercise had a continuation in exercise 4.4 where they told us, so in exercise 4.4, they're telling us that x0 is equal to 9. By the way, because I remember right now. Yes, because Ivo asked us if smaller x and bigger x are the same. Yes, it just sometimes my keyboard is stuck on big letters, sometimes stuck on small letters, so it kind of depends on how I find it. I'm sorry if that's confusing, but they mean the same thing. It's just an x variable in an equation. Okay, so the continuation of this exercise. They're giving us x0 is equal to 9, and they tell us solve the equation, which means that we have to find in our final version the alpha so that this solution of the recurrence relation is forever true. And we have x0 is equal to 9. Just like we did in exercise 4.1, I will replace the initial value in this equation, knowing that t will become 0, because t, remember, is the indice of your variable x. Therefore, if x0, t is equal to 0. So I will replace all of this information in my equation and I will solve for alpha. Therefore, x of t will be x of 0 equal to 9. 9 is equal to alpha multiplied by 3 to the power of my t, which is 0, plus 2 multiplied by 2 to the power of my t, which is 0. Therefore, 9 will be equal to alpha multiplied by 3 to the power of 0 is equal to 1, plus 2 multiplied by 2 to the power of 0 is equal to 1. 2 multiplied by 1 is equal to 2. Therefore, alpha will be equal to 7 because it's going to be 9 minus 2, right? So it means our solution will be xt is equal to 7 multiplied by 3 to the power of t plus 2 multiplied by 2 to the power of 7. And did I miss anything? 7, 3 to the power of t. No, that's it. And this is your final version of your solution that you can find out once you've already known one of the values of your x's. So this is the final version of the solution. And this is how we will look for alpha. Was it clear now for everybody? Did we all understand how to solve this kind of recurrence relations? Do we understand how we solve for alpha afterwards if we have an initial value? Do we understand how to work with the algorithm, more importantly? Yes, perfect. I'm really happy to hear, guys, because there's these exercises are really easy, and I think there's quite a few of them in the exam. So it's really important if you understand how to do one or two. If you keep practicing and get a little bit used to the table of the solutions, then we're all good to go.